Okay, like I said, Michaelis-Menten derivation was a huge advance in providing an explanation for why enzyme catalyzed reactions seem to behave the way they did, right? But there was a problem. It was kind of a serious problem conceptually. Before we go there, let me just point out a couple more things about nomenclature here. So in honor of Michaelis and Menten, this complex, this enzyme substrate complex, is often referred to as the Michaelis complex, right? You hear people say the Michaelis complex. What they mean is that enzyme substrate complex, right? In addition, what's frequently done in thinking about these mechanisms is to eliminate this sort of K2, right, in terms of like that sort of step subscript 2, and replace this with a constant called Kcat, right? Which essentially you're talking about the rate constant for doing chemistry. It's in this scheme, the unimolecular rate constant at which substrate is converted into product, right? So another way to write the Michaelis equation, right, would be to say, all right, in that case, what this would say is that the initial rate is equal to Kcat times the total enzyme times the substrate times Ks over Ks plus S. Or another way is that Vmax is equal to Kcat times the concentration of total enzyme. Okay, but there's like I said, there's a problem, right? And the problem has to do with this guy right here, with K sub S. Specifically, the problem is that Michaelis and Menten, in their derivation, that solved the problem of how we set up a straightforward and simplified scheme. The assumption that they made was that the enzyme substrate complex here was in thermodynamic equilibrium, right? Or that the enzyme substrate complex was in thermodynamic equilibrium with the free enzyme and the substrate. And the problem is that in some cases that turns out to be true. In a great many cases, even for simple enzymes, that's wrong. It can be shown, and this was even people were beginning to realize this even within a few years after Michaelis-Menten and colleagues came up with this basic equation. People were realizing that that assumption is violated. All right, that's like, oh man, but that really helped so much. Now what do we do? Well, along came in 1925 a couple of other great early biochemists by the name of JBS Haldane, or G.E. Briggs, and JBS Haldane. And what Briggs and Haldane recognized was that, okay, that assumption of thermodynamic equilibrium, that's frequently wrong. But even for those enzymes where that's wrong, the following still turns out to be true, that if you go and you do experiments with those enzymes here as a function of time, and we're looking here at rate, right? And remember, we're under these large substrate excess conditions. What turns out to be true is at early times in the reaction, those reactions are linear, right? So here, in this case, we would be increasing the substrate concentration, right? Even enzymes that violate the assumption of thermodynamic equilibrium still behave this way. They show linear initial rate behavior, which was one of the things that we were sort of, is built into this assumption of the Michaelis-Menten equation. How could that be? Well, what Briggs and Haldane recognized was that there's a way for one to build a scheme around this basic simplified scheme, enzymatic species description or kinetic scheme, under these initial rate large substrate excess conditions that does not require thermodynamic equilibrium for the Michaelis complex, but still results in linear initial rate behavior, right? Okay, to understand that, I need to rewrite, I'm gonna rewrite the scheme using the specific rate constants again, right? So remember, the simplified scheme we came down to was this one, K sub 1, K minus 1, that bimolecular formation of the Michaelis complex, followed then by this unimolecular K2 formation of enzyme plus product. And Briggs and Haldane said, everything that got us here, that still holds, right? That's still good. But what they recognized was that thermodynamic equilibrium for the enzyme substrate complex here, you can only achieve equilibrium, oops, equilibrium here between the enzyme substrate complex and free enzyme and substrate is only achievable if K2, the rate of doing chemistry, is much, much smaller than K minus 1. Thermodynamic equilibrium here between these guys is only possible if the rate at which chemistry happens is far slower than the rate at which the enzyme substrate complex can fall apart. And that makes some sense if you think about it. If the enzyme binds a substrate and does chemistry much faster or on a time scale similar to which the enzyme substrate complex could dissociate, the enzyme substrate complex never gets a chance to equilibrate, right? Under those conditions, chemistry is happening too fast relative to the rate that the complex could fall back apart. So you never achieve, under these conditions, you never achieve thermodynamic equilibrium. And this was the problem. There are reasonable large number of enzymes for which this is true. And yet, this still applies. All right, so the question is, how? How is that possible? All right, well, what Briggs and Haldane recognized was that even if this is true, the observation here of linear initial rate behavior means something else has to be true. What they recognized was that if we're thinking again about the rate change of product with respect to time, we know from everything we've discussed and from this observation here that that's a constant, right? This is just equal to that initial rate. Well, if that's a constant, what that means is that this has to be constant. K2 or Kcat, however you want to think about it. Let's just, since I switched back to K2, times concentration of the enzyme substrate, this has to be a constant. That can't be changing with time. If that can't be changing with time, the following has to be true, which is that the rate of change of the Michaelis complex, the enzyme substrate complex with time, has to be equal to 0. Doesn't have to be in thermodynamic equilibrium, but at the initial rate measurement window in large substrate excess, the concentration of ES of the Michaelis complex can't be changing with time. And it can't be because we know this is true. All right, if that's true, we can look back at this scheme here and we can say, well, what would that look like, right? And you think back to the way I did that unimolecular reversible rate equation, we apply a similar set of logic. We've got to pipe in and we got to pipe out. This concentration isn't changing, which means the rate at which stuff is coming in versus the rate at which stuff is coming out has to balance. Okay, well, based on what we talked about last time, we can write that down. The rate at which stuff is coming in All right, that's pretty easy. That's just the binding, right? So that's just the rate at which we make the enzyme substrate complex. That's just K1 times concentration of enzyme times concentration of substrate. That's my pipe in. I got 2 pipes going out. Okay, that would just be equal minus then K minus 1 times the enzyme substrate complex. All right, there's our pipe going back that way, going back in the opposite direction. Minus K2 times the enzyme substrate complex, right? So there's our pipe going this way. Okay, that's cool. But if that has to equal 0, what that means is that those input and output rates have to balance. And another way to say that if we're not at thermodynamic equilibrium, but we've got this species whose rate is not changing with time, that means that the enzyme substrate complex is in a steady state, right? Formally, it's not at equilibrium, but its state is constant as a result of balanced input and output rates. It's in a steady state. Oh, all right. Well, that's cool, because now I can combine this idea here with the idea we used before that related the total enzyme concentration to just the free enzyme plus the enzyme substrate concentration, right? We can put these two together, right? And eliminate the Michaelis complex variable in that rate expression before. All right, well, the first thing to do, let's just like move things around because we got a 0 here. So let's just take this guy and sort of reload it, right? We can say, we know that we can write this as K1, concentration of enzyme, concentration of S, has got to just be equal to K minus 1, concentration of ES, plus K2, concentration of ES, right? Pretty straightforward. And now I can go substitution happy, rearrange this expression for the total enzyme and substitute that in to that expression, which would then give me something that looks like this. We'd have K1, right? Concentration of substrate times concentration of E0 minus concentration of ES, going to just be equal to K minus 1, concentration of ES, plus K2, concentration of ES, right? All right, that's pretty easy. All I got to do now is just solve that for concentration, rearrange it, right? Which is pretty straightforward, and then solve it for concentration of ES. So I'll just write that out here. So we can rearrange this expression, say, multiply through concentration of E0 minus concentration of ES times concentration of S. Move that constant K1 over to the other side, group these guys together. Whoops, dropped a 1. K minus 1 plus K2 divided by K1, right? Concentration of ES. Cool. Now all I got to do is solve that for concentration of ES. That's pretty straightforward. So now concentration of ES has got to just be equal to concentration of E0, concentration of substrate, divided by concentration of S plus K2 plus K minus 1 over K1. Huh. That's cool. Because remember, again, what is our fundamental observable? Production of P with respect to time. We're at initial rate conditions, large substrate excess, so it's a constant. And that's just described by that expression there, which means we've solved for, once again, we've solved for the thing we can't easily specify, this concentration of the Michaelis complex. So now my expression for the initial rate is real simple. It's just, again, V0 equals K2 concentration of ES, which now substituting here is just K2 concentration of E0 concentration of S divided by, I'm going to write this slightly different place, -1 over K1 plus concentration of S. Huh. What if I do this? What if I say, that's kind of messy. So what if we just define this guy? We're going to give it a name. We'll call it Km. K sub m is going to equal K2 plus K minus 1 over K1. I can now rewrite that expression thusly, where V naught, my initial rate, is just equal to K2 concentration of E0 concentration of S over Km plus concentration of S. And doing the substitution for K2 equaling Kcat in this simple mechanism, we can write this back out as Kcat concentration of E0 concentration of S over Km plus concentration of S. Does that look familiar? Just at least in terms of the basic form of that equation? It ought to, because if you look back to the last lecture that we derived the Michaelis-Menten equation, right? The Michaelis-Menten equation was simply that we could write this out as Kcat concentration of E0 concentration of S divided by Ks plus concentration of S. So it's exactly the same algebraic form, right? Kcat over E0, again, that would equal Vmax, equals Vmax in both cases, right? Which means the so-called steady state derivation, which is the Briggs and Haldane's mechanism that we just went through. The idea that you don't have to assume thermodynamic equilibrium. All that has to be true is that the Michaelis complex is in a steady state, right? That its concentration doesn't change as a function of time. It's balanced by the rate at which it's made and the rate at which it decays. You end up in exactly the same place with one wrinkle, which is that Km, in this case, equals this ratio of these rate constants, right? These forward and reverse rate constants, K2 plus K minus 1 over K1. But if you think back to what Ks was equal to, right? You look back up in those notes, what was Ks equal to? It's basically equal to a dissociation constant, right? It was equal to K minus 1 over K1. And I look at those two here, right? What are the conditions in which this expression, the Ks expression here, turns into, or the Km expression is equivalent to that expression, the Ks expression? It's pretty obvious, right? When K minus 1, right, is much greater than K2, if that's the case, right, in this expression here, when this is the case, K2 becomes insignificant. And under those conditions, Ks then is equivalent, Km is then equivalent to Ks, right? So we come sort of full circle all the way back around. So the overall expression that one wants to remember, of course, is the same in both cases. The initial rate is simply equal to Vmax, concentration of, excuse me, look at this. Again, Vmax times concentration of substrate divided by Km plus the concentration of substrate, where we know Vmax is equal to Kcat times the concentration of total enzyme in solution, and Km equals that K1, all right, excuse me, God, writing this down wrong. Equals K2 plus K minus 1 over K1, right? And this expression, Km, approaches an equilibrium constant when the rate of chemistry is significantly slower than the rate at which the enzyme and substrate complex can dissociate. Okay, so in the next lecture, we'll talk a little bit about how you deal with steady state enzyme data with respect to getting at these values, which are usually the things you want, right?